We will finish the presentation of CSEC Multiple Choice Practice Paper 3 with Part D. These are the problems that will take us from number 46 to number 60. The point A, 3, 5, is mapped onto A prime, 3, negative 5, by a single transformation represented by the matrix T. We need to determine the matrix T. And of course, we have all the choices right here on the left-hand side that we will be using to determine the matrix T. With the exception of a translation that is represented by a column vector that is added to the point under transformation, all other matrices of transformation are 2 by 2 matrices that are multiplied by the point that is being transformed. So apart from translation, of course, which is a column vector or column matrix that will be added to the point, every other matrix of transformation will be a 2 by 2 matrix that we will multiply by the point that is being transformed. So what we expect 3, negative 5 to be, we expect 3, negative 5 to be the result of multiplying this point by the matrix, or maybe this one. So we have the choices and we need to do some analysis in order to determine which one is actually correct. Whatever the matrix T is, it will be used to multiply A, as we have discussed before. We will give the matrix T a general form and use it to multiply A. So this will take the place of our matrix T that we use to multiply A. It is 2 by 2, right, to multiply the point A, and the result is 3, negative 5. So which one of those matrices that we have in the choices will be our correct matrix? So we are taking a look at the first one by replacing our general matrix T by the first one that we have there, which is 1, 0, 0, 1. A is the identity matrix. When it is used to multiply any other matrix, the product is equal to the multiplicand. The answer would have given the point 3, 5. A is not correct. This matrix is what we call the identity matrix. We usually symbolize that matrix by writing it as a capital I. So that is our identity matrix. When the identity matrix is multiplied by another matrix, the answer is equal to that same matrix. Therefore, we would expect that if this matrix multiplies 3, 5, that the answer will turn out to be 3, 5. The answer is identically equal to the matrix that it is being multiplied by. Therefore, we expect that our answer would be 3, 5. So we have 3, negative 5 here. The first matrix, 1, 0, 0, 1, is not the correct answer. The other one, what do we know? In our typical matrix of transformation, there are only 2 non-zero elements. This one has 3. B is not correct. Typically, when we have the matrix of transformation that we typically use for the CSEC, those matrices usually are given with 2 non-zero elements. So we have this one and this one probably, or we may have the subordinate diagonal. But to have 3 non-zero elements in a typical matrix of transformation, this one cannot be correct. So we are sure that this one is not right. We need to have only 2 non-zero elements. What about that one? Candidates who are familiar with multiplication, or if not, common sense should tell that the 2 negative numbers in the leading diagonal of the matrix should have the effect of changing the signs of the 2 numbers, resulting in negative 3, negative 5. Option C is not correct. We have a negative number right here and a negative number right here. So we expect that if we multiply this matrix by this one, then we will have negative 3, negative 5. That is not the case. So we imagine that this one cannot possibly be the correct answer. As a matter of fact, we multiply row by column. So we have negative 1 multiplied by 3 and then 0 multiplied by 5. So negative 1 multiplied by 3 will give negative 3. So we are sure that we are not correct. We do not have a negative 3 right there. We are only left with option D. By the process of elimination, option D is correct. And we are sure that option D is correct if and only if all of the other options are actually incorrect. So if we have used correct principles to deduce that option A, option B, option C, those are not correct, then we are sure that the correct answer is option D. However, we will use matrix multiplication to prove that option D is actually correct. So we are multiplying. What do we have? 1 multiplied by 3 and 0 multiplied by 5. We have row multiplied by column. There we are multiplying the top row by the column. And this will give the top element of the resulting matrix. As a matter of fact, we only have a single column, so we will take these rows in turn to multiply that single column. So 1 multiplied by 3, 0 multiplied by 5. We have 1 multiplied by 3, 0 multiplied by 5. So our animation is also showing which element is multiplied by which. Then what do we do? Keeping that same column matrix in mind, we go down to use the single row that we have left, which is this one, is the only one that we have left. We will use this row to multiply the single column that we have right there. What do we know? 0 multiplied by 3, negative 1 multiplied by 5. And if we simplify, what do we get? Right here, this one will be eliminated because 0 multiplied by 5 is 0, so we will only have 3. And here we have 0 multiplied by 3, that will be gone. So we will have negative 1 multiplied by 5, and that will give negative 5. So we will have, this one is out, 3. This one is out, negative 5. There we have it. Option D is correct. There is no doubt that the point could have been multiplied by each option in turn in order to determine which one will actually work. This would have been a lengthy process. I guess that is one of the reasons why the examiner chose to make option D the correct answer, favoring those who are familiar with matrix multiplication and matrices of transformation. Those candidates should be able to examine the options and solve the problem in a matter of seconds. The examiners imagined that candidates would just multiply this by the point, then multiply the next one in turn, right, and eventually going down in sequential order to D. Therefore, if we think that the person is going to go in that order, the correct answer is D, then that candidate would have used up the maximum amount of time possible in solving that problem. Well, if candidates are familiar with multiplication of matrices and matrices of transformation, then one should be able to just take a short look and determine the correct answer. And the examiner, in the way that they have organized this problem, is favoring those candidates who have learned their lesson well. and would have taken advantage of all opportunities. 2 fair dice are tossed 9,000 times, and the numbers shown are recorded. How many times should you expect to get a sum of 6? How would you approach such a problem? In order to determine the expected numbers of sum of 6, we need to find the fraction of the number of times that a sum of 6 is expected and multiply that fraction by 9,000. That fraction will be the probability of obtaining a sum of 6. We know that when you toss those 2 dice, we have a wide variety of possibilities. We need to determine 1, the number of possibilities, and 2, the number of possible sums of 6. If we know that, then we will know, or we will be able to determine what fraction of the total number of possibilities will the number of sums of 6 be. If we are able to do that, then we will take that fraction and multiply it by 9,000, and we will get not the number of sums of 6, but the expected number of sums of 6, which of course is far way different from the actual number of sums of 6. May not be different in number in the final analysis if it is done 9,000 times, but in theory there's a great significance, or there's a significant difference between the two. That is, there's a significant difference between the actual number of sums of 6 that we get and the expected number of sums of 6. What will we do? We will take a systematic approach to find all possible sums, because we need all possible sums and we need the number of sums of 6. All the possible numbers on one die will be placed in the first row of the table, and all of the possible numbers of the other die will be placed in the first column. So we will put the numbers in. Those will be for one die, and those that we have in the vertical will be for one die. Then we will find the possibilities, all possibilities, by adding. And we are going to, of course, take a systematic approach as we have discussed before. So all of the possible sums will be determined according to the sum of numbers in the rows and columns as shown. And when we say as shown, we mean the animation will show. So there we have the first. All the numbers in the first row of sums will be this one plus all those on the first die. Then we move to 2, and then we add 1, 2, 3, 4, 5, 6. By adding in that manner, it is possible to determine all of the possible outcomes. We will not leave any out, and we are sure that we will not repeat any. So we will take 4 and add 1, 5. 4 plus 2 is 6. 4 plus 3 is 7. 4 plus 4 is 8. 4 plus 5 is 9. 4 plus 6 is 10. Then we go to the other row. 5 plus 1 is 6. And so on and so forth. And we will do that until the entire table is exhausted, at the end of which time we would have determined all possible sums. And if so, that we have discovered all possible sums, it is possible for us to determine the possible sums of 6. There is the region that we are concerned with, because after completing the table, one candidate might be confused or might just be in a hurry and use the entire table and find all of the 6's. We have highlighted the possible sums or all the possibilities with that green rectangle. The region of sums contains 36 items. There are 6 rows and 6 columns, and of course, if it is 6 by 6, 6 multiplied by 6 is equal to 36. We have 6 columns and we have 6 rows. Within the region of sums, there are 5 6's. How many 6's do we have? We have 5. There are therefore 5 sums of 6 out of 36 possible sums. This represents a fraction of 5 over 36. There are 9,000 tosses. For the expected number of sums of 6, we multiply the fraction of sums of 6 by the total number of tosses. So the number of sums of 6 will be 5 over 36. That is a fraction of the total that the number of sums of 6 will represent. And that we will multiply by the total number of tosses. It is tossed 9,000 times. So let us look at those sums of 6. We have them right there. So take a second look. 1, 2, 3, 4, 5. So we have 5 possible sums of 6, and that we will divide by the total number of possibilities, and we have 36 of them. There's our fraction, 5 over 36 to be multiplied by 9,000. This is simple. 9,000 divided by 9 is equal to 1,000. 36 divided by 9 is equal to 4. Then we take 1,000 and divide that by 4. We get 250, and that we multiply by 5. That is 1,250, and that is done very quickly. Let's see if we can take a second look at that. 9 into 9,000 will give 1,000. 9 into 36 will give 4. So we will have 1,000 there, and we will have 4 here. 4 into 1,000 is 250. That 250 we will multiply by 5, and we will get 1,250. We can reduce the fraction mentally, and that we have done. The correct answer is option A. The use of the table is not a must, but it places the solution of a problem beyond doubt. If candidates can make the calculations without it, they should. It is just that the visual effect provided by the table is very evidential. The sums that result in 6 are as follows. 1 plus 5, 5 plus 1, 2 plus 4, 4 plus 2. Because of the pairs, 1 plus 5, 5 plus 1, etc., one may be tempted to place the 3 in pairs. This will cause them to have 6 sums instead of 5. So what do? They say, well, we have 2 of these, we have 2 of these, so we must have 2 of the other. And they use 6. So we are sure that we have only 1, but they make this mistake and they use 2, ending up with a total of 6. So they use 6 instead of 5, and the simplification of that, they would have received 1,500, which is option B. And they might be sure that the answer is correct, when in fact it is not. So by just making that simple mistake, one might get an incorrect answer that is represented in the options here, and that can possibly give you a wrong answer. The length and width of a rectangle are 9 centimeters and 5 centimeters respectively, each measured to the nearest centimeter. The range of possible values of the perimeter of the rectangle is, let's see. This problem requires us to make use of the knowledge and understanding of what is meant by a value rounded to a particular unit. Especially of importance is that the lower bound is half of a unit away, while the upper bound is 0.4 of a unit away. If the upper bound is a half of a unit away, or we make it then half of a unit away, it will be rounded to the next unit above. That means that since we are talking about 9, if we start at 8.5 rounded, we will get 9. But if we put 9.5 rounded, we will get 10. So the maximum that we can go is 9.4. Take note, 9 centimeters and 5 centimeters measured to the nearest centimeter. 9 centimeters and 5 centimeters are measured to the nearest centimeter. Let us therefore take note of the maximum and minimum values of the length and width that could have been rounded to 9 centimeters and 5 centimeters. We are taking a look at the maximum and minimum numbers that could have been rounded to 9 and 5. For the length, the maximum is 9.4, the minimum is 8.5. For the width, the maximum is 5.4, and the minimum is 4.5. Use the maximum values to find the maximum value of the perimeter. What is the perimeter equal to? The perimeter of a rectangle is equal to 2 times the sum of the length and the width, or 2 times all of length plus width. We need to add the length and the width, then multiply the result by 2. We are looking at the maximum value of the perimeter now, so we are using the maximum values of the length and width. We are substituting those into that expression. Where we have length, we put 9.4. Where we have width, we put 5.4. Adding them together, we get 14.8. Then we multiply that by 2. I think we'll get 29.6 centimeters. What do we do next? Move to the minimum. So use the minimum values to find the minimum value of the perimeter. P is equal to 2 times the sum of the length and the width, as we have just used. Substituting the values that we have there, 8.5, 4.5, right. Finding their sums, 13. So 2 times 13 is equal to 26. But are we conclusive as to what the answer should be? The perimeter will range from the minimum value to the maximum value. In the same way that the length and width were written to the nearest centimeter, the perimeters need to be written to the nearest centimeter. That is, the one that is not already to the nearest centimeter. One is to the nearest centimeter already, which is this one, but this one is not to the nearest centimeter. We will write that correct to the nearest centimeter by, of course, rounding off to the nearest centimeter. So there we have it, 30 centimeters, and we have a minimum of 26 and a maximum of 30. And which one is correct? The range of possible values of the perimeter is from 26 centimeters to 30 centimeters, and it is represented by option C. There are 2 serious considerations The first one, if the upper bound is taken to the half of a unit, it will be rounded to the unit above, as we have discussed before. For example, if instead of 9.4 we used 9.5, the length would have been rounded to 10 instead of 9. It is therefore appropriate to use 9.4. And the second one is, the length and width were given to the nearest centimeter. The perimeter also needs to be rounded to the nearest centimeter. Lovely problem. The point 2, -3 is translated by the vector -3, 4. The coordinates of its image is, what is the coordinate of the image of that point, translated by that vector? Before solving the problem, let us take a look at the principles on which its solution is based. The matrix of a translation is a column vector that is added to the point that is being transformed. So, the matrix of transformation, which is this vector, as long as we are translating, it is going to be added to the point that is being transformed. That means it will be added to 2, -3. First, identify the point that is being transformed. Where is it? There we have it, 2, -3. That is the point that is being transformed. What do we do next? The matrix, and we have in bracket there, vector. Which one? Okay, let us say the vector in line with the statement of the problem. So the vector of transformation is required to be added to it. So we are going to add the matrix or the vector to that one. And all we need to do is determine the sum. The sum of the two will result in the image. And what is the image? How do we find that? We say 2 plus -3 is equal to -1, and -3 plus 4 is equal to 1. So we have -1 first and 1 second. -1 first and 1 second. So -1, 1. The correct answer is option A. That's all there is to it. In finding the image of the point is written as a column matrix. In calculations, vectors are usually written as column matrices. How can the point 2, -3 be classified as a vector? Yes, we have it right here, 2, -3. How can it be classified as a vector? Or is it? The point is not classified as a vector. Instead, the point is said to have position vector. The position vector of a point is the vector that joins the origin to that point. The x and y components of the vector are simply the x and y coordinates of the point. This 2, -3 is written right here as a vector. As a matter of fact, it is not really written as a vector. It has position vector, and this is the position vector that it has. And we are adding the vector to it, and this is the result. And do not forget that the vectors are written in the form of column matrices. So the same principles that we use to add matrices will be applied right here. And no doubt will give the appropriate answer. Which of the following could describe the mapping f such that x goes to x plus 3? That's the first one. And then we have f such that x maps to 2x plus 1. But we are talking about this mapping. 1 is mapped to 3, 2 is mapped to 5, and so on and so forth. After developing the skills of using a mapping to arrive at an algebraic representation of a function, one may be able to look at pretty much any mapping and write down its algebraic representation. But until then, let us look at some basic steps that one may take. So if you are skillful at it, you just look at it, and in a few seconds you are able to determine the algebraic representation of that mapping. But let us say that you are not that skilled. Then we will give you some tips right here. Let us see if there is a constant value that may be added to each element of the domain D that will result in its image in the range R. So let us put in the domain and the range. We are attempting to see if we can find one number, like say 7, that is added to this one and results in this, added to this one and results in this, added to this one, and so on. So let us see if there's a single number with that capability. Alright, so to get 3, we say 1 plus 2 is equal to 3, and 2 plus 3 is equal to 5. What does that tell us? That tells us that there is not a fixed number that we add over here in order to get this one. Say for argument's sake then, this one is not possible to be correct, because we are saying all we need to do all the time is add 3 and we get the answer. So add 3 to this one, we get this one. Add 3 to this one, we get this one. Add 3 to this one and we get this one. That is what this one is saying, that there's a fixed number that is added to the ones in the domain and we will get the one in the range. We know that is not correct because we add 2 in the first case and 3 in the second case. In the first case 2 is added, in the second case 3 is added. We cannot say that a constant number is added because it is not the same number that is being added each time. Therefore, we move merrily on. We may do an investigation for a constant multiplier. So we are going to look for a constant multiplier. So let us take a look at it. What do we know? We have the 1 here. 1 multiplied by 3 is equal to 3. But to get 5, we need to multiply 2 by 2.5. So 1 multiplied by 3 is 3. 2 multiplied by 2.5 is 5. So we do not see immediately a constant multiplier. So we may do an investigation of the constant multiplier, but turns up null and void. In the first case, multiplication is by 3. And in the second case, multiplication is by 2.5. There is no constant multiplier that we can see. It is also clear that the elements are not related by a square or cube relationship. On the next slide, we will take a look at further steps that may be taken in order to develop the algebraic relationship. Let us move merrily along. We see that we do not have a constant number being added, and we do not see that a constant figure is being multiplied. So we move merrily on. Another investigation shows that we do not have a square or a cubed relationship. That means 1 multiplied by 1 does not give 3, 2 multiplied by 2 does not give 5, so we do not have a square. Neither if we cube 2, we will not get 5. So those other relationships are out. The next step that one should take is to find the difference between consecutive numbers in the range. Since all of those have failed, what do? Find the difference between consecutive numbers in the range. We have 3, 5, 7, 9. Difference between 3 and 5 is 2. Between 7 and 5 is 2. Between 9 and 7 we have 2. What do we know then? Well, it does not necessarily seem obvious, but what do we say? Each one is equal to 2, so we are on to something. Having 2 here as a difference, that's significant. But how significant? And What is the significance? Because of the constant increase by 2, the mapping has to do with multiplication by 2. This is not obvious. To show this, let us use another mapping in which there is a constant increase by 2. So because the difference all the time is by 2, we know that we are talking about multiplication by 2, but it is not so obvious. But let us do something. We are going to take another mapping in which the difference between consecutive numbers in the range will be 2. So we have 2, 4, 6, 8. Going up by 2 each time. We have 1, 2, 3, 4. No doubt. Then we see that 1 multiplied by 2 is 2. 2 multiplied by 2 is 4. 3 multiplied by 2 is 6. 4 multiplied by 2 is 8. Therefore, we can conclude that it has something to do with multiplication by 2. It is usually the case when the difference between the consecutive ones, we have 2. 2 all the time. We now see that each element in the range may be obtained by multiplying its associated element in the domain by 2. And that is for this particular function. And we are saying that it is related to this. All because the difference between consecutive here we have is 2, and the difference between consecutive here we have is 2. It is more obvious here that each one has something to do with multiplication by 2, because it is directly equal to the one that we have here. But it's not so obvious. But we are saying that they are related. What is the relationship? In the original mapping, we are sure that we need to multiply by 2. What adjustments need to be made in order to obtain the numbers? Right, so we have multiplication by 2 here. And, of course, we are saying it's related to this. But how is it related? Look at each one of those. What do we know? 2 is going to 3. 4 is going to 5. 6 is going to 7. And 8 is going to 9. We can see a direct relationship. What is that? If we simply multiply by 2, as we have done in the second mapping, the elements in the original mapping may be obtained by adding 1 to each of the results. So we simply multiply by 2 here. Then what do we know? To go over here, we add 1 to 2, we get 3. Add 1 to 4, we get 5. Add 1 to 6, we get 7. Add 1 to 8, and we get 9. Therefore, after multiplying by 2, we need to add 1. That is all this is saying. The algebraic representation may therefore be found by multiplying by 2, then adding 1 to the result. This turns out to be 2x plus 1 and is represented by option B. That one. So we see that when we have a constant difference of 2, it has something to do with multiplication by 2. And further investigation shows that if we multiply by 2, then add 1, then we have our correct answer, as we have shown. So let us do another illustration. Let us take another one. There we have another one. There is no obvious connection between an element of D and its associate in R. Proceed by finding the difference between consecutive elements of R. So we will do that again. We do not have any obvious relationship that we can determine in a second, 20 seconds. We cannot determine any obvious relationship. So we find the difference. And when we find the difference is 3. What do we say if the difference is 3? We say that the difference is 3 tells us that it has something to do with multiplication by 3. There's a constant difference of 3. Each element may be found by multiplying its associate by 3. Like what we have right here. But after doing that, what follows? Because by multiplying by 3, we definitely did not get all of these. Find the relationship between each element and its counterpart in the original expression. What do we know? 3 goes down to 1. 6 goes down to 4. 9 goes down to 7. 12 goes down to 10. We are subtracting 2 each time. Those elements may be obtained by subtracting 2. The expression is therefore f is such that x maps to 3x minus 2. Some candidates may want to try out each expression by substituting the elements of D in turn, in order to see which one will generate the correct element of R on every single occasion. That will definitely be the correct one, no problem. If you say, okay, you have the mapping down there, substitute in this expression all the elements of D. Put in 1, then you put 2, then you put 3, you put 4. Then you get all of the answers. Then this mapping would turn out to be the correct one. There's no harm in doing that. Some candidates may be very skillful at arriving at the algebraic representation from a given mapping, or some may even be familiar with certain number patterns and will be able to identify the correct algebraic representation immediately. So one might be skillful. If you are skillful, you will have no problem identifying the answer immediately. But on the other hand, you have some students who just know certain number pattern and they are able to just look and say, okay, because of the pattern, this one is the correct answer. The method used in solving this problem may be lengthy in its presentation. However, after the skill is developed, it may be executed in a few seconds rather than spending many minutes using trial and error in arriving at the answer. In using trial and error, the speed at which a problem is solved is dependent on which of the expression is tried first. For fear that the answer is D, some candidates may not want to go in sequential order. For the sequential candidate, the time spent solving the problem is heavily dependent on the position of the correct answer. Option D will consume the most time. R is a right angle and P is equal to Q is equal to 6 centimeters. The length of R in centimeters is, we need to determine the length of R. We have the information already that P is equal to Q, that is equal to 6 centimeters. The triangle is right angled and two sides are equal. This makes it a right-angled isosceles triangle. In all such triangles, the hypotenuse may be found by multiplying the length of the short side by the square root of 2. If we have a right-angled isosceles triangle, the hypotenuse may be found by multiplying the length of one of the short sides by the square root of 2. P is equal to R is equal to 6 centimeters. There we have 6 centimeters for each one of them. To find the length of R that turns out to be the hypotenuse, we need to multiply 6 by the square root of 2. So multiply 6 because that's the length of the short side. Both short sides are equal. So we have R is equal to 6 times the square root of 2. The result is definitely correct, but no option looks exactly like it. We need to make some adjustment. C and D are obviously not correct. They are obviously not correct because they do not have anything to do with square root. We know that the answer has something to do with square root, so we are sure C and D cannot be correct. We need to write our answer as a single square root. Which number is 6 the square root of? So that is the first question that we are asking in order to determine the answer in this form. As a matter of fact, this is a method that I'm using of solving the problem, which of course is also in Richard James Mathematics Resources, Steps to Success in Mathematics. The method of solving a problem in which you ask yourself a question and you answer the question. In solving the entire problem, you may ask as you go along certain questions, and as you answer those questions, you are taking steps to solve the problem. First question is, which number is 6 the square root of? We need to write our answer like this or this. We have 6 times the square root of 2, and we are sure that that one is correct. We need to get it in that form. We also need to write this in the form of a square root. What number is 6 the square root of? We need to replace 6 with that number. So 6 is the square root of something. We will replace that 6 that we have right here with the square root of something. 6 is the square root of 36. We replace 6 with the square root of 36. So we have square root of 36, square root of 2. In mathematics, when we have expressions, numbers coming one after the other, not separated by any arithmetic operation, the arithmetic operation that we assume is multiplication. We are actually multiplying square root of 36 by square root of 2. We are using another rule. The product of the square roots is equal to the square root of the product. We have a product of square roots that is equal to the square root of the product. So that is equal to the square root of 36 multiplied by 2. 36 multiplied by 2 is equal to 72. R is the square root of 72. Option B is correct. So the correct answer is option B, the square root of 72. We are not done yet. Let us now demonstrate that the hypotenuse of a right-angled isosceles triangle is equal to the short side multiplied by the square root of 2. That is what we are demonstrating right now. And we need to be reminded that we are talking about a right-angled triangle. So the triangle must be right-angled. Then it must also be isosceles. The short sides are equal because we have isosceles triangle. Isosceles triangle has 2 equal sides. So let us generally refer to the length of the short sides as A. So there we have it. Pythagoras says that the square of the longest side, which is the hypotenuse of a right-angled triangle, is equal to the sum of the squares of the 2 short sides. We are using Pythagoras Theorem to determine the hypotenuse. And it says that the square of the longest side is equal to the sum of the squares of the 2 short sides. The 2 short sides are A. And the hypotenuse squared is equal to A squared plus A squared. What is A squared plus A squared? A squared and A squared, we have like terms. We are combining those like terms. And what do we get? 2A squared. So A squared plus A squared is equal to 2A squared. Make H the subject by finding the square root of both sides. There we have it, the square root of both sides. The square root of a product is equal to the product of the square roots. That's another rule. The square root of a product is equal to the product of the square roots. So we have square root of 2A squared, 2 multiplied by A squared. That means, and we have, that is equal to the square root of 2 multiplied by the square root of A squared. And since it is multiplication, we do not need to put a sign between the 2 square roots. When there is no sign coming between, the arithmetic operation that we always assume is multiplication. Square and square roots are inverse operations and will eliminate each other. Multiplication is commutative, and the order in which we write the square roots does not matter. So let us make use of this statement in writing the next step to this problem. So we have square root and square. Those are inverse operation and they will eliminate each other. So we will have on this side only h. Here we have a similar situation. We will have only a. Right. And then we need to be reminded that multiplication is commutative. So we may reverse the order in which we have these two. So we will have h is equal to a times the square root of 2. Like that. And that's all there is to it. The hypotenuse may be found by multiplying a by the square root of 2. As long as we have a right-angled isosceles triangle, the hypotenuse is equal to the short side multiplied by the square root of 2. After that, we will find the hypotenuse of each one of these. Every single one is a right-angled isosceles triangle. The length of each short side of the right-angled isosceles triangle are given. We may therefore write down the length of each hypotenuse. So, let us write down the length of each hypotenuse. How do we do that? It's simple. We have right-angled isosceles triangle. So, the hypotenuse is equal to 3 times the square root of 2, short side multiplied by the square root of 2. What do we imagine here? 10 multiplied by the square root of 2. And here, no doubt, 8.5 multiplied by the square root of 2. 15 multiplied by the square root of 2. 0.7 multiplied by the square root of 2. It does not matter. As long as each one is a right-angled isosceles triangle, the length of the hypotenuse is equal to the length of the short side multiplied by the square root of 2. O is the center of the circle of radius r. Angle OAB is a right angle. What is the area of the shaded region? So we have our shaded region right here. What is its area? We are making use of the fact that we have what? R here, and no doubt we will have R here also. And it is said that this angle that we have right here is a right angle. So this angle is a right angle. That is, AOB is a right angle. The shaded region is what remains when the right angled triangle is removed from the sector. So this shaded region that we have here, we will see what happens in a short while. See, we have a sector and we are removing a right angled triangle. So the area is what remains when we take the right angled triangle, and of course it's right angled isosceles. So when we take this right angled triangle from the sector, the shaded region is what remains. See, we have the shaded region that's equal to what we get when we take away the right angled triangle from the sector. That's what the shaded region represents. The sector is a fraction of the circle. The fraction is given by its associated angle divided by the angle of one revolution. So, since it is a sector, it is a fraction of a circle, and the fraction that we are going to take of the area of the circle will be dependent on the fraction that its associated angle represents. That is, the fraction that this angle represents of the entire 360 degrees revolution. So there we have the fraction. That is the fraction that we need to multiply by the area of the circle. The area of the circle is pi r squared. No doubt, pi r squared, we have it right there. From that, we need to subtract the area of the triangle. The two sides that are equal to the radius of the circle are at right angle to each other. They may therefore be treated as the base and height. This causes the base and the height to be equal to r. So we have a right angle triangle that we are taking out from the area of the sector. So we have the area of the sector here. We will subtract the area of the right angled triangle. Since it is right angled, and you know that the area of a triangle is half base times height, further, the base needs to be at right angle to the height. So we have no problem since this angle is a 90 degrees angle. So what do? We write down the area to be half r squared, because it is a half r multiplied by r, and r multiplied by r is r squared. So a half r squared, that is the area of the right angled triangle. We are subtracting that area from the area of the sector. And what do? 90 over 360. We know that 90 is a quarter of 360, but we may reduce this by a common factor of 90. 90 into 90 is 1. 90 into 360 is 4. So it turns out to be a quarter of pi r squared. And this one turns out to be a half of r squared. R squared is common. So we may take the r squared as a common factor, and we may also take a quarter as the other common factor. So we need to factorize this. We see right here that we have a quarter r squared, a quarter r squared, a half, and so on. So we are sure that we need to factor one of those fractions out. We are opting on this occasion to take out a quarter. After taking out a quarter, then we may demonstrate on subsequent slides that we are correct in taking out a quarter. So we are factorizing by taking out, as we can see, it is blatant right here that r squared is common, and we will also take a quarter as a part of that common factor. In which event we have a quarter r squared pi minus 2. Which one is the correct one? We have it right here. The correct answer is option B. We will take a second look at the factorization. Most candidates will not have a problem taking out a common factor of r squared. However, they may find the fraction a little bit blinding. So they have no problem seeing that we can take out this r squared. It is obvious that r squared is a common factor, but taking out another factor of a quarter might be a little bit blinding, especially arriving at this 2 right here. But we will demonstrate that we are correct in a minute. The most basic application of factorization is find a common factor and divide each term in the expression by the common factor. The common factor is a quarter r squared. So we will take out a quarter r squared, and what do we do with a quarter pi r squared? We divide by the common factor, a quarter r squared, and what do we do with the negative a half r squared? We divide that by the common factor, a quarter r squared. In the first case, what do we know? There's no problem seeing the quarter cancelling, quarter divided by a quarter, those will take care of each other, and there's no problem seeing r squared taking care of r squared. Those will have a cancelling effect on each other. Both numerator and denominator contains pi r squared, so those will be eliminated in the first fraction. All that is left is pi. In the second fraction, we can see r squared cancelling. No problem seeing that. No problem. We then have half divided by a quarter. We know that there are 2 quarters in a half. So the answer is 2. Or we may consider dividing by a fraction to be multiplication by its reciprocal. So we can just say, well, we half divided by a quarter. We are sure that 2 quarters make a half. So we are sure that the answer is 2. R squared will cancel with r squared. No problem seeing that is 2. Or we may say that if we have a half divided by a quarter, that is equal to a half multiplied by the reciprocal of a quarter. And we know what is going to happen. 2 into 4 is 2. No doubt. That is our correct answer. We have proven that if we go the legitimate road of factorizing from the most basic principle of factorization, the answer that we have there would have been proven to be legitimate. The area of the right-angled triangle could have been found by making use of the formula A is equal to a half AB sine C. That is, the area is equal to a half AB sine C. And let us see what those mean. That is the area that we are talking about. The area of the right-angled triangle. A is equal to a half AB sine C. The triangle is right angled. Therefore, the angle C is equal to 90 degrees. A and B are the 2 sides that form the angle C. They are actually the radius of the circle. Both of them are equal to R. So, half AB sine C, what does that mean? Half the product of 2 sides of a triangle multiplied by sine of the angle that the 2 sides form. That is, the sine of the angle that these 2 sides form. So in this case, A is equal to R, B is equal to R. So A multiplied by B will be equal to R multiplied by R. That's equal to R squared. Sine of C. So we have a half R multiplied by R, sine of 90 degrees. R multiplied by R is R squared. Sine 90 is equal to 1. And any number or expression multiplied by 1 is equal to itself. So this is going to be multiplied by 1. And anything multiplied by 1 is equal to itself. We have a half R squared. Alright. How do we know that sine 90 is equal to 1? In the olden days, we had to know the sine, cosine, and tangent of popular angles in regular and surd form. On the next slide, we will have 2 tables that give the sine, cosine, and the tangent of those angles. Sine 90, in the olden days, every student of trig knows that sine 90 is equal to 1. We use them so often that they became second nature. We would not try to memorize the table. We use this sine, cosine, and tangent of those angles so often that knowing them became natural. So we did not have to sit down and study, memorize, going through, doing a lot of repetitions in order to get information into our brains. We use them so often that knowing them became natural. What about those? We have 2 forms. We have 1 over square root of 2 or square root of 2 over 2. Those are equal. We have 1 over square root of 3 or root 3 over 3. Right. The fractions with the square roots in the denominators represent the originally derived form. Mathematicians do not like to write denominators with square roots or radicals. The irrational square roots are therefore removed from the denominators by a process called rationalization. Square roots of numbers that cannot be written as a whole number, finite decimal, or a combination of those are called irrational numbers. So these are irrational numbers. Well, let us see if we have any examples. Yes, we do. Square root of 2, square root of 3, square root of 10 are irrational. They cannot be written as a whole number. They cannot be written as a finite decimal. And they cannot be written as combinations of finite decimals and whole numbers. Therefore, they are called irrational. What about the square root of 144? Square root of 144 is equal to 12. We know that it is equal to a positive or a negative 12, but this time we are taking the positive square root. So the square root of 144 is 12. Because it can be written as a whole number like that, we are sure that 144 is rational. The square root of 2.25 is 1.5. We have a whole number right here and a finite decimal right here. So we are sure that the square root of 2.25 is also rational. What about that one? That symbol is called infinity. It refers to a number that is so large that the number of digits that may be used to represent it has no end. So that is what infinity is. So large, cannot be represented by a finite number of digits. Infinity is usually obtained by dividing another number by 0. Dividing by 0 on your calculator will give a fatal error because that number does not really exist. So that number does not really exist because it is so large that it really isn't real. And dividing by 0 on your calculator will give you a fatal error because its intended answer is actually infinity. Let us take a look at how we arrive at those horrible looking numbers. We are talking about square root of 3 over 2, 1 over root 3. We talk about 1 over square root of 2, square root of 3. Why do we have sine, cosine, and tangent of certain angles actually equal to these? Let us see. That is your very good friend. There we have an equilateral triangle in which all sides and angles are equal. That is what we mean by an equilateral triangle. In an equilateral triangle, all sides and angles are equal. Let us say that the sides are equal to 1 unit. The angles will be 60 degrees each. That's what we have in an equilateral triangle. All angles are equal to 60 degrees each. But we are saying, in this particular case, we are saying that each side is equal to 1 unit. Can be anything as long as they are all equal. But the angles need to be equal to 60. So we have our angles 60 each and 1 unit each for each side. If we dropped a vertical from the uppermost vertex, it will bisect that angle and be the perpendicular bisector of the horizontal side. There we have it. So this line bisects this angle. We'll have 30 on each side, and down here we have a half a unit on each side because the entire length is 1 unit. So we have half of 1 here and half of another right here. So half of 1 on both sides. And the angle is bisected 30 degrees each. This line is a perpendicular. So on this side we have one right angled triangle, and on the other side we have another right angled triangle. The two new triangles are right angled. Sides 1 will be the hypotenuses. This one is going to be the hypotenuse of this right angled triangle, and this one, side 1 in this particular setting that we have right now, will be the hypotenuses. Each short side is equal to a half, as we can see. One short side is a half, the other is a half. Pythagoras theorem may be used to find the length of the vertical, which turns out to be the remaining short side of each right angled triangle. We will use Pythagoras theorem to find this one. Will turn out to be the remaining short side of this triangle and also the remaining short side of this triangle. Let's go. Remember that when we are applying Pythagoras theorem in finding one of the missing short sides of a right angled triangle, we say hypotenuse squared minus the length of the other short side square. What is the hypotenuse? 1 unit. What is the short side? A half of a unit. So 1 squared minus a half squared. 1 squared, which is 1, minus a quarter. What is 1 minus a quarter? 3 quarters. When we find the square root of 3 quarters, what? The square root of 3 is irrational. So we will just write that as the square root of 3. And the square root of 4 is 2. So we will have what? A is equal to the square root of 3 over 2. Right. Root 3 over 2. So that is the length of the other short side. And this is the region that we are in. Finding what? The trig ratios of 30 degrees. So any one of these triangles will suffice. Let us find the trig ratios of 30 degrees. 30 degrees, we are going to take this triangle, hopefully. Right. Do not forget, sine is equal to opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent. And we are doing that off the 30 degrees angle. We are focusing on the 30 degrees angle. Well, it doesn't matter which angle we are considering, the hypotenuse will be the same. The longest side of the right angle triangle. Now what about the other one? Opposite. The one that is opposite to 30 degrees is this one. So this side becomes the opposite. The one that is facing on the opposite side of, or on the other side of the angle, that one is the opposite. Then we need also to include the adjacent. That is the adjacent, the one that is beside the angle, alongside or adjacent to the angle. That is the one that is called adjacent. And of course, right now we are focusing on the 30 degrees angle. And the first thing we need to find is sine of 30. What is sine of 30? This one, sine of 30. Sine is what? We have it here, opposite over hypotenuse. Opposite over hypotenuse, a half divided by 1. Right, and anything divided by 1 is that same thing. So a half divided by 1 is a half. And what about cosine? Adjacent over hypotenuse. This one over this one. So we have square root of 3 over 2 over 1. Anything divided by 1 is equal to that same thing. Root 3 over 2 divided by 1, root 3 over 2. And the other one, opposite over adjacent. Opposite, a half, over adjacent, square root of 3 over 2. Right. And we have a fraction divided by a fraction. We invert and multiply. So invert the fraction that is in the denominator and multiply. So we have a half multiplied by 2 over the square root of 3. The 2's will cancel. 2 will cancel with 2. The 2's will cancel, and we will have 1 over the square root of 3. And that is how we arrive at 1 over the square root of 3. Good. Let us take on another one. I think that will take on 60 degrees because we have that same triangle with a 60 degrees angle. So we'll take on 60 degrees. Right, 60 degrees. Let us find the trig ratios of the 60 degrees angle. Opposite over hypotenuse, that's for sine 60, and the trig ratios are the same. But if we are talking about the 60 degrees angle, no doubt the hypotenuse will be the same. It does not matter. The hypotenuse is always the longest side. Right. Opposite. That one is the opposite. On the other side of or facing the angle or opposite to the angle. And we need to include the adjacent, the one that is beside the 60 degrees angle, alongside it or adjacent. There's no doubt that this hypotenuse is also adjacent to the 60 degrees angle. But it also, or we may say that it has its special name already. So we include the adjacent right there. Next, sine 60 is opposite over hypotenuse. The opposite is root 3 over 2 over 1 for the hypotenuse. So we have opposite over hypotenuse, root 3 over 2 divided by 1, and anything divided by 1 is itself. And we move down to the adjacent over hypotenuse, a half over 1, and that is equal to a half. Opposite over adjacent, we have root 3 over 2 over a half. Invert the fraction that is in the denominator and multiply. The 2's will cancel again, and we have square root of 3 to be divided by 1. Anything divided by 1 is itself. We have square root of 3. The 45 degrees angle belongs to the right-angled isosceles triangle. Now we are going to take a look at the 45 degrees and its associated trig ratios. That one belongs to the isosceles right-angled triangle. There we have our right-angled isosceles triangle. Since the triangle is right-angled, one angle is already equal to 90 degrees. It is isosceles. The other two angles must be equal. The remaining angle, which is 90 degrees, must be shared equally between those two. So 90 to be shared between the other two angles equally, 90 divided by 2 is 45. So one angle is already 90. 90 is left to be shared equally between those two, and each one will no doubt be 45 degrees. Let us say that the two equal sides are each 1 unit. Right, we are in our comfort zone now, or we should be in our comfort zone right now. Let us say that each one of those short sides is equal to 1 unit. Pythagoras Theorem may be used to find the hypotenuse, although we should be able to write it down from the principles explained in the solution of the problem before this, which is number 51. Okay, so the hypotenuse is equal to a squared plus b squared, and of course each short side, and we know that one short side is 1 and the other is 1, so 1 squared plus 1 squared, which is of course 1 squared plus 1 squared is equal to 1 plus 1, which is equal to 2. So we are talking about the square root of 2 eventually. The length of the hypotenuse is square root of 2. Do not forget that a few minutes ago we were taking a look at right-angled isosceles triangles, and we know that the hypotenuse is equal to the length of a short side multiplied by the square root of 2. 1 multiplied by the square root of 2. We know that if we multiply 1 by something, the answer is going to be equal to that same thing. So no doubt we have the square root of 2 right there. And we could have just written it down from the previous knowledge that we have. Then we are on to it. Let us write down the trig ratios of 45 degrees. So there we have our 45 degrees, and same again. Opposite over hypotenuse for sine, and so on. So let us go ahead and write down the sine of 45 degrees. Opposite over hypotenuse. But before we do that, we could label the triangle. The hypotenuse is the longest side. And since both angles are 45 degrees, it does not matter. We might just still write down an opposite. The opposite and the adjacent will be the same length. And the adjacent we have right there. First one is opposite over hypotenuse. It doesn't matter. Say this one. Opposite is 1. Hypotenuse is square root of 2. 1 over the square root of 2. That's all there is to it. And that is what we have right here. 1 over the square root of 2. And the cosine is the same, because we have adjacent over hypotenuse. The opposite and the adjacent are equal to 1. 1 over the square root of 2 again. What about the tangent? The tangent opposite over adjacent. 1 divided by 1, and that is equal to 1. So tan of 45 degrees is equal to 1. Good. The right angle triangle in which the other two angles are 90 degrees and 0 degree cannot be correctly represented. However, for the angle that should be 0 degree, let us draw it very small. The side opposite to it should be equal to 0 and hence invisible, impossible to be drawn. But let us make it very short, just for illustration. The other two sides will be 1 unit each. So there's our very thin right angled triangle. We have to do it this way in order that we can get in some form of understanding of how to determine the trig ratios. So we are at angle 0. It is not convenient to label the sides as before, but let us write down the trig ratios of 0. We have them there, opposite over hypotenuse. The hypotenuse and the adjacent are equal, because this is the angle that we are talking about. Opposite is 0 over hypotenuse, which is 1. 0 divided by 1 is equal to 0. What about cosine? Adjacent over hypotenuse. This is the hypotenuse. It is equal to 1, and the adjacent is also equal to 1. So what do we have? 1 over 1, which is equal to 1. And for the tangent, we have opposite over adjacent. We have 0 over 1. And that, no doubt, should give us 0. We will then move merrily along and find the trig ratios of 90 degrees. Opposite over hypotenuse. This is the angle that we are talking about. Opposite 1 over hypotenuse is 1. So sine of 90 is equal to 1. What about cos of 90? This is the angle. Adjacent is 0. Hypotenuse is 1. 0 over 1 is equal to 0. And finally, tan of 90. tan of 90. This is the angle opposite to this one. We have 1. And the adjacent is 0. So we have 1 over 0 that does not exist. Right? Is equal to infinity. So there we have somewhat of an explanation as to how we arrive at the sine, cosine, and tangent of some of the more popular angles. The table shows the distribution of ages of 25 children. What is the mode of the distribution? So what is the mode? What do we mean by mode? The mode is the item of data that occurs the most times. It is associated with the highest frequency. The frequency on this occasion is represented by number of children. So we are going to take a look at the number of children, which is the frequency, determine the highest value that we have right there. Identify the largest number in the row that represents the number of children. Number of children, the largest one, which is the frequency. So the largest value of the frequency is 6. The mode is a value that is associated with that one. So identify its associated value in the age row. There we have it, 11. The mode is 11. Mode is equal to 11. The correct answer is option C. The table shows the distribution of the ages of 25 children. What is the probability that a child chosen at random is at least 13 years old? The probability that an event will occur is determined by dividing the number of events that will give a favorable outcome by the total number of events. In finding the probability, we need to find out the number of those that will give us the answer that we need. And that we will divide by the total number. At least 13 years old. So all of those that will be in the set that represents what? Those that are at least 13 years old. Those will be a part of our favorable outcome. The ones that will give a favorable outcome are those that are at least 13 years old. No number can be smaller than the least. So if it is the least, we will be talking about those that are 13 and above. We are therefore talking about those that are 13 years and older. And this is the region that we are talking about. Those that are 13 years and older. So 13, 14, 15, 16. All of these we are talking about. All of these will give us a favorable outcome. So those will give us a favorable outcome. We will divide the sum by the total number of events that are already known to be 25. We have it right here. Distribution of 25 children. And of course, if we add all of these, we will get 25. So we need to divide by the total number of events. So dividing by 25, what happens? We get all of these. I think that we can add these quite easily because of a pattern. 5 plus 3 is 8 and 4 plus 4 is 8. 16 over 25. The correct answer is option D. On this occasion, we need to determine the median score. That's what we need to find. The median score. The distribution is the same as in the two previous problems. But on this occasion, we need to find the median score. The median is the middle item in a sorted list. When there is an even number of entries, the median is the average, which is the mean of the two middle numbers. So if we have an even number of items, then we are sure that we will have two middle entries. The median will be the average of those two middle entries. We just add them and divide by 2. There appears to be 6 entries. 6 divided by 2 is equal to 3. The two middle entries are the third and the fourth entries. So we are just taking an approach, like a blind approach to the problem, neglecting a lot of the details, and we are attempting to solve that problem just by what we might probably call an erroneous approach. So we are just solving the problem off the top of our heads, and we need to find the median. We say we have 1, 2, 3, 4, 5, 6 entries. Right. So 6 divided by 2 is 3. So we will take the two middle entries and divide by 2. So there we have all 6 of them. The first temptation is to look at the already ordered list of scores and choose the two middle items, 13 and 14. 13 plus 14 divided by 2 is equal to 13.5. Actually, 27 divided by 2, which is 13.5. We need to be aware of the fact that there are scores in the list that occur more than once. The number of times that those scores occur are determined by their frequencies. Our calculation must not be without taking that fact into account. Besides, the statement of the problem has declared that there are 25 children. So we are sure that we do not have 6 entries. We have 25 entries. So we need to take that into account, along with the fact that some of those entries occur more than once, like we have them here, 11 occurring 6 times and 15 occurring 4 times. Let us see if a correct approach to the problem will result in a different answer from the one received. If it does not, the problem will be a serious indictment on the examiners, with an expected erroneous approach resulting in the correct answer. So if we get the answer, this same answer, by using a correct method, then that will not speak positive on the behalf of the examiners, because we will use an incorrect approach and still get the same answer. But let's see if the examiners will redeem themselves. There are actually 25 entries. 25 divided by 2 is equal to 12.5. The 13th entry will be the median. So we are in search of the 13th entry. We have 25 entries, which 25 children. The middle will be the 13th entry. We are now in search of the 13th entry. At the end of the first column, we would have passed the first 6 entries. So we are searching now for the 13th entry. Right, so let us go. We have 6 entries here. So by the time we have gone past this, we would have gone past 6 entries. Therefore, at the end, we would have passed 6 entries. In the next column, there are an additional 3 entries. Therefore, at the end of the second column, we would have exhausted 6 plus 3, which is equal to 9 entries. 6 plus 3 is 9, so we pass 6 here, then we pass another 3, so we pass 9. Next, we have an additional 5 entries. The last entry in the third column will be the 14th in the entire list. So we have the 9 now that we will add another 5 to here, and we would have exhausted, or we would have gone past 14 entries. And we are looking for the 13th entry. Well, it is obvious that if the 9th entry is here and the 14th one is here, then the 13th one must be inside here, which will cause the 13th entry to actually be 13. Right. The last entry in the second column is the 9th overall. Right here we have the 9th overall. The last entry in this one, we have the last entry in this one is the 9th overall. Therefore, the first entry in the third column will be the 10th overall. The first one in here will be the 10th entry overall. So if the last one is the 9th here, the first one of the next one will be the 10th. Therefore, in here we will have what? The 10th, the 11th, the 12th, the 13th, and the 14th entry. So the 13th entry will be inside here. As previously discussed, the median is the 13th entry. It is located in the third column. The item of data in the third column is 13. The median is 13 and is represented by option C. The median is 13. As we can see, finishing up here, we have the 9th. When we get into here, we have the 10th, 11th, 12th, 13th, and 14th. The 13 is inside here. The 13th entry is 13. And that is represented by option C. As indicated by the frequency row, some scores occur more than once. Let us use this fact along with the specific frequencies to write down the scores. And of course, do not forget that we are in search of the 13th entry. There are 6 11s. 11 occurring 6 times. 1, 2, 3, 4, 5, 6. Move merrily along. Now we have 3 12s. 3 12s. And then what? Now we have 5 13s. There are all of 5 13s. 1, 2, 3, 4, 5. There are 25 elements in the list and we need the 13th one. The middle of the list. The median. We are certain to have passed the middle of the list by now. Right. So we should be past the middle of the list by now. Let us now locate the 13th entry. First, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th. 13. So the 13th entry, we have it right there, and that turns out to be the 13. And 13th entry is the 13th, and that turns out to be the median. So the median is equal to 13. Good. The examiners have vindicated themselves. The answer is not the same as the one obtained by an erroneous approach to the problem. So this says a lot of positive stuff for the examiners. The diagram shows the angle of depression of a point x from z. If x is 10 meters from y, the height yz in meters, that's this one, the height of yz in meters is. The trig ratio usually associated with angles of elevation and depression is tangent. Based on that fact, we may conclude that the correct answer is option B. That's the one. It does not take more than a second to determine that answer. But what do? However, we may solve the problem actually to verify that we are correct. We know that angles of elevation and depression are alternate angles and are therefore equal. We usually call them Z angles. They are alternate angles, Z angles, and they are therefore equal. So we have the angle of depression given here. From here, we have an angle of elevation. These two are equal because they are alternate angles, or Z angles. That angle is 30 degrees also. We need to determine the height YZ in meters. The side YZ that we need to know is opposite to the known angle. Where is YZ? There, opposite to the known angle. This is the known angle, and YZ is opposite to that known angle. The known side is adjacent to the known angle. This is our known side. Relative to this angle, it is adjacent. Right, in solving a trigonometrical problem, we need to take note of the known values that we have, and also the relationship between what we are trying to find and the known values. Therefore, in the beginning, we said that the side that we want to find, which is YZ, is opposite to this known angle, making use of the known. The trig ratio that contains opposite and adjacent is tangent. So we have opposite, we have adjacent, and the trig ratio associated with opposite and adjacent is tangent. Also, it is important for us to take note of this known side relative to this angle, and that is what we have done in determining that this side, or stating that this side, is actually adjacent to the known angle. So the trig ratio that contains opposite and adjacent is tangent. Tangent is equal to opposite over adjacent. But notice how we write it in this case. Opposite over adjacent is equal to tan 30. And there's a reason for doing that. What will we do next? Since we know opposite adjacent equal to tangent of 30, because we are talking about the opposite that we do not know and the adjacent that we do know, we are about to substitute the values right here. So we will have what? YZ over 10. So we have it. YZ over 10 is equal to tan 30. And we will transpose, making YZ the subject of the formula. What do we have? Transpose the equation by multiplying by 10 on the right hand side. We are multiplying by 10 on both sides, in which event 10 will be eliminated from this side, and we will multiply the right hand side by 10. So YZ is equal to 10 tan 30, and that is what we have right there. We have verified that the correct answer is actually option B. ABC is a triangle in which AD is equal to BD is equal to CD. And we need to determine the size of angle ABC. That is angle ABC. The one that is located at the vertex B. This one. Those marks indicate that the length of the line segments are equal. The statement of the problem also declares this. These marks that we have are saying that these line segments are equal. And we have it also mentioned in the statement of the problem. So because of that, what do we know? This causes the two smaller triangles to be isosceles. Now we have this large triangle that is comprised of two smaller ones. So the two small ones will be isosceles. There we have them. On this side, we have this is equal to this. So this triangle is isosceles. And we have on this side, this is equal to this. So this triangle is also isosceles. Because of that, in the first isosceles triangle, the two equal angles will be called x. So in this one, we have two equal angles. They are opposite to the two equal sides. So this angle is x, and this one is x. And then, this big angle that we have here will be the result of subtracting these two from 180 degrees, because angles in a triangle add to give 180 degrees. Although this one will not play any further part in determining the value of the angle ABC. We know that we have angles in a triangle 180 degrees, and we have two of them right here. They are equal to x, so the other one will be what remains of that 180 degrees. In the second triangle, the equal angles will be y, and we have an analogy right there, where we have two angles y and y. So we have 180 minus 2y right here for the records. But these two angles will not play any further role in the solution of the problem. Focusing on the big triangle, all of its angles will add to give 180 degrees. In this big triangle, all of the angles will add to give 180 degrees. That is, let me put that down. And we are talking about this angle, this one, and this one. Those are the three angles that make up the large triangle. We are going to add them. So we have x to be added to x and y, which is x plus y, which is to be added to y. So we have x here, we have x plus y there in the middle, and y at the end. Add them together, we get 180 degrees. We have two occurrences of x right here, and two occurrences of y. No doubt, 2x plus 2y is equal to 180 degrees. Divide the entire equation by 2. There we have it. Each term in the equation is divided by 2. So the 2's will cancel here. We have x. The 2's will cancel here. We have y. 2 into 180 is 90. So we have x plus y is equal to 90 degrees. So this is what we have. X plus y right here, which is ABC. The angle ABC is what? This one right here, x combined with y, x plus y. That is the one that we need to find. And here we have determined that x plus y is equal to 90 degrees. The angle ABC is the sum of x and y. The correct answer is therefore option B, 90 degrees. The circumference of a circle is 132 centimeters. Given that pi is equal to 22 over 7, the radius of the circle in centimeters is, and we need to find the radius of the circle. What do we know? The circumference of the circle is given by the formula, well, it is the circumference of any circle is 2 multiplied by pi multiplied by r, 2 pi r. In this problem, the value of the circumference is already given, and the value of pi is also given. Circumference is 132 centimeters. The value of pi is 22 over 7. We will therefore substitute for pi 22 over 7, and for the circumference we will substitute 132. The circumference 132 will go right there. Pi is 22 over 7, and we will replace that. R will therefore be the only unknown in the resulting equation, which is what we need to find. We need to determine the value of R. It is the only unknown that we have right there. No problem. One equation with one unknown, that is solvable. The expression may be transposed, leaving R alone on the right-hand side. Those by which we multiply on the right, we will divide on the left, and those by which we divide on the right, we will multiply on the left. So we are dividing by 7 here, we will multiply by 7 here. We are multiplying by 2 and 22. We will divide by the product of 2 and 22 on the left-hand side. There we have it. The 7 that is divided on this side is multiplied here. Those that are multiplied on this side, we divide here. Reduced by a common factor of 44, if we can see that. So 2 times 22 is 44, and we know that 44 into 132 will be 3 times. 3 multiplied by 7 is equal to R. R is equal to 21 centimeters. The correct answer is option C. I can quickly see that 44 is a factor of 132, and that the denominator is equal to 44. You can see that the denominator is 44, 2 times 22. But I can also see that 44 can go into 132 without leaving a remainder. If you cannot see those big steps, then reduce the fraction in your own good time. 132 is a multiple of 12. From your multiplication table, you should know that 12 multiplied by 11 is 132. This means that 132 is a multiple of 4. Since 132 is a multiple of 12, and of course 12 is a multiple of 4, then we are sure that 132 is also a multiple of 4. But we have it here already. That is what? 132 is a multiple of 11. It is a multiple of 11. It is a multiple of 4. It must be a multiple of 44. So we could make this calculation in our minds very quickly. So 132 is a multiple of 44. So we can divide 132 by 44. And we could reduce this fraction quite quickly. We have an algebraic expression in the form of an equation. And we need to make Q the subject of the formula. This is a problem in which we need to change the subject of the formula to Q. This one. P and R will be eliminated from the right-hand side. On the right-hand side, we have P, we have R, accompanying Q. We need to eliminate these from the right-hand side. Eliminating the denominator from the right-hand side will result in the left-hand side being multiplied by R. So eliminating this will result in R being multiplied on the left-hand side. So we have PR is equal to P plus Q. PR is equal to P plus Q. Next, we need to eliminate P. Eliminating P from the right-hand side will result in P being subtracted from the left-hand side. So PR minus P is equal to Q. Write the proposed subject on the left-hand side. That's all we need to do now. Q on the left-hand side, PR minus P on the right. So Q is equal to PR minus P, and that is all there is to it. The correct answer is option B. All vegetarians are healthy. That means I must be healthy. George is not healthy. Therefore, George is not a vegetarian. Which Venn diagram illustrates this information? Now, H is the set of healthy people, V the set of vegetarians of which I'm included, and U is the set of all people. All vegetarians are healthy. The set of vegetarians must be contained inside of the set of healthy people. All vegetarians are healthy. So if you consider the vegetarians, all of them will be inside of the set of healthy people, and that is what we will demonstrate first. So the set of vegetarians will be contained in the set of healthy people. George is not healthy. Therefore, George will be placed outside of the set of healthy people, and hence outside of the set of all vegetarians. So George is placed outside of the set of healthy people, hence outside of the set of vegetarians. George will be placed outside here. The set of vegetarians will be inside the set of healthy people. George is not healthy. Being away from the set of healthy people, he is sure to be away from the set of all vegetarians. So there we have George outside. The option that has the set of vegetarians inside of the set of healthy people and George outside of the set of healthy people is option D. So we are looking for the set of vegetarians inside the set of healthy people. This is one of them, and this is another, right? But we need George to be outside of the set of healthy people. So he will be outside, not inside of the set of vegetarians. He will be outside of the set of healthy people, and hence outside of the set of vegetarians. So the correct answer is option C.